Good afternoon, everyone. Welcome to the session on Civil Engineering and Renewable Energy 2. My name is Miguel Nóbrega from the University of Minho in Portugal, and I'll be the chair for this session. Move to the second presentation of the session. It will be given by Mr. Licheng Zhu from UCD, University College of Dublin. And the title of his presentation is Validation of a 3D Computational Fluid Dynamics Model and Wind Tunnel Test Results for the Queen's Ferry Crossing, Mesh Sensitivity and Domain Study. Please go ahead.
Hello everyone, welcome to my presentation. My name is Licheng and I'm from UCD. So, long-span bridges are vulnerable to the effect of wind. The study of bridge aerodynamics is essential in ensuring the safety and acceptable performance. Typically, there are three methods used for the bridge aerodynamic design. They are the field test, wind tunnel test, and CFD simulations. For the field test, it is reliable, but in the meantime, it is extremely time-consuming, and the sensors installed on the bridge are very expensive. The detection may also affect by the traffic or animal, etc. Also, is impossible to imply for the bridge design stage. As for the wind tunnel test, it is used for a very long time by the industry, and it's a common way for engineers to get relatively trustable results. It's reliable for most cases, but since the limitation of the size of the testing facility, the wind tunnel test is using a scaled model. So it's totally different from the real bridge condition. Even so, the wind tunnel tests are not cheap at all, and the issues like Reynolds number inconsistency, instrument interference, and so on could also affect the results accuracy. Compared to those two methods, CFD simulations are much more flexible. Firstly, you have the control of the level of accuracy and cost. And it depends on the different purpose of your work. You can work on different schemes for the different level of accuracy. Secondly, in wind tunnel test, experimental results are normally collected from limited sampling points. If you need information of a certain point that is not sampled, you need to either repeat the test or interpolate the data from other sampling points. Well, in CFD simulations, you can extract information from all the fields within the domain. And CFD, it's non-intrusive, so there's no sensors, no interference. Validation is very important for the CFD simulations because poor configurations can lead to unphysical results. Then let me give you a brief introduction of the Queen's Ferry Bridge. The Queen's Ferry Crossing Bridge connects the traffic between Edinburgh and Fife. It used to be the longest three-tower cable-stayed bridge in the world. The bridge carries about 24 million vehicle journeys a year, so it's very much a major traffic connection. The simulations are based on this bridge, and I want to thank Arab and Jacob for kindly share the internal test report with us. So here is the geometry of my simulation. It is a 1/40 scaled 3D model with a bus and truck symbol on it. It's created in AutoCAD and exported to STL files so that it can work in OpenFOAM. Since the location of the Queen's Ferry Crossing Bridge is an area prevailing southwesterly winds, in wind tunnel test, we have tested a model with the other three different yield angles. So therefore, I get the configurations based on it, as you can see in the figures. The wind tunnel test is performed in a closed circle wind tunnel. It got a saddle of 36 long, 40-meter wide, and 4-meter high. I built a smaller domain to save some computational power. Simulation results have shown that the flow can fully develop in this scale. So I will talk about the domain study later. Let's move on to my mesh scheme. I work on 3 different kind of mesh schemes. Generally, it's a coarse mesh and a medium mesh and a fine mesh. Here in this slide, I'm introducing the best one of them, fine mesh. So the meshing procedure begins with generating the background mesh. I created 12,800 cubic cells of 0.25 meters weights, as shown in the figure. So the area close to the bridge model are refined to level 5, which bring the size of cell to 0.00625 meter. And the area around vehicle is further refined to level 7. Also, I set 7 buffer layers between adjacent levels to make the cell size changing smoothly. As the boundary layer's thickness varies with the flow conditions, the Y plus value is mainly considered as a reference for the quality of the mesh scheme. To make the simulation accurate enough, the goal is to try to achieve the Y plus value less than 1. So I added 7 layers of cells with an expansion ratio of 1.2 to resolve the boundary layers. The overall thickness of the boundary layer is 0.0005 meter, which is close to the dimension of the level 7 cells. And overall, there are no distorted cells. The average non-orthogonality is 7 degrees. The maximum skewness is below 4. And the Y plus value of the bridge surface is less than 1. So it's a good mesh, and the total cell number is around 100 million. Here is a summary of the 3 kind of different meshes. Generally, they are different in the level of the refinement. And the fine mesh got the best refinement of the bridge. The coarse one got a lot of part of the bridge broken or distorted. So it's a main reason for the inaccuracy, and you can see that the Y plus value, the fine one, is the best one. It got Y plus average Y plus value of 4. The wind velocity is, as for the boundary condition, the wind velocity is 4 meters per second, and turbulence mixing length is 0.7. This two is exactly same as the wind tunnel result, and the value of K and omega is calculated by these 2 equations for the initial value, and it will be calculated by the transport equation. K value and the K value of the bridge surface is said to be very small instead of 0, because it's to try to avoid float point problem. Aerodynamic force acting on the vehicle are recorded and then calculated by the equation I showed here, which is provided by the wind tunnel report. So the figures show the results comparison between the wind tunnel and the CFD results. We can see that the main difference of the results are shown on lift coefficients. Here is a big difference, and for the drag coefficients, it's small difference, and they are similar. The percentage difference, the different percentage between the two can be more than 180%, which happens here, the coarse mesh and the blue one, wind tunnel. So generally, the average different percentage of the fine mesh is only 14. And for the medium and coarse one is 24 and 35. So the results indicate that the fine mesh scheme is the best one, and it's necessary to use that. A large domain and a full domain, which is exactly same as the internal domain size I investigated. Domain 1 is the domain that I used in the previous studies. Domain 2 is a larger one, which has a size of 20 meters long, 7 meters wide, and 4 meters high. Domain 3 is exactly same as the internal. So all the 3 studies were applied to the geometry of zero yield angle and the mesh schemes and all the other parameters of the fine mesh I used. Results in figure AC shows that the drag coefficients are similar. However, from the lift coefficient here, we can see that the results show different, and it needs more mesh refinement for the larger domain, because it uses a lot of power on the background mesh. So we can see that when the turbulence can fully developed, the domain size used in the modeling was not significantly affect the simulation results. So it's okay to reduce the size of the domain to considering the need to be efficient with the computation powers. Here is the sliced flow visualization of the domain 1 simulation. You can see that here, the turbulence is fully developed. So basically that's all. Thank you for your listening and thank you for your time. Please be free to ask me any questions.
Thank you, Licheng, for the nice presentation. We have already a question from one of the attendees. First of all, an excellent work. And the Y+ plot on the bridge surface looks fantastic. But the question is, how long did the simulations take to converge? I believe you shown a slide where you show the differences in terms of computational time for the coarse and the refined mesh in comparison with the reference one, but I believe you didn't provide the actual times. And this is the question: how long it take to converge? Okay. For instance, the reference mesh you have presented.
Okay, thank you. That's a good question, and it's different for the one I showed in the picture. That one, it takes me like almost 4 days to converge because I use 120 cores because the number of cells is really huge, so it takes a long time. And for the others with different yield angles, and the yield angles leads to the different number of cells, so it takes even more longer because the cell number is a lot more than the zero yield angle one. So on the average, like it takes 4 days to
4 days
for each simulations.
Okay, that's nice. Thank you.
Thank you.
So I believe there are no other questions, and we are on time to finish the. Sorry, we have another question. Have you used K omega SST model?
Yeah.
Is that the model I've used?
Yeah.
Why have you used the model? Which were the motivations to use it? And the other question, just to finish, is how they compare with the other turbulence models?
Yeah, I didn't compare it in this study because in this study I want to use the K omega SST because it's a like a better one. I used the K epsilon one to compare it with it, but it's not as good as this one. So in this study I just use K omega SST. Okay.
So thank you for the clarifications. Thank you for the questions, and we're on time to move for the next presentation.